So I decided to do a different talk than the one from the workshop. And we're basically moving away from observations and completely into theory. So the idea behind this talk is a simple idea. I'm trying to explore if there are other tectonic settings apart from plate tectonics that could enhance or can enable habitability in other planets. And this would be a particularly important mechanism for planets around M stars that have a habitable zone in a place where tidal heating can happen continuously. I want to acknowledge that this work was done with the help of 2 undergraduates, 2 undergraduates, to other things. So we talked about plate tectonics already in this, actually in the workshop mostly, and we think plate tectonics has been actually quite important for Earth's evolution, and it's the only planet that we know has plate tectonics. In particularly, we think that it enables the carbon-silicate cycle to take place. On the Earth, and the carbon-silicate cycle is the way that the planet regulates its surface temperature over geological time. So, and it happens because you have water that reacts with carbon dioxide in the atmosphere, producing this carbonic acid that can leach out calcium and magnesium ions that can then make its way down to the bottom of the ocean, and at that point can interact with the carbon in the ocean and sequester it into a rock. This constant carbonate here that then gets deposited into the bottom of the ocean and then can be carried down by subduction. Some of it will go back again into the atmosphere, but some of them will be moved onto the deep mantle and closing the cycle. And the reason this works as a thermostat is because this weathering reaction is very sensitive to temperature. So if the temperature in the atmosphere is hot, because maybe the sun is very hot, this weathering reaction is very fast. So it sequesters carbon, sequesters CO2 into the rocks, and then it drives down this greenhouse gas, making the planet cool again. And then if you have very cold conditions, like as a snowball Earth, you don't have this weathering. You shut down that weathering cycle, whereas you still have volcanic outgassing of carbon, so you end up putting enough to then restore back balmy conditions. And this was proposed by Walker in 1981, and then was taken by other authors, including Casting for planets around other stars. And at the time, it was heavily the continental cycle was the one that was heavily important. But even a few years later, Walker recognized that sea weather could also be taking place and serve perhaps as another sink to the carbonate cycle. And for example, Brady Giselson did experiments to show that it could have a temperature dependence law, and Gillies and Coogan and others have looked at isotopes that show that it is possible that this weathering has a temperature dependence, therefore, even on its own can create a cycle, a negative feedback cycle needed for restoring equilibrium. So the idea that, the simple idea that I want to put forward is, could there be another tectonic setting that would play the same role as plate tectonics does on the Earth? And so we need to break down into simple things what does plate tectonics do for this cycle. And the important ones is that, first of all, it closes the cycle, I told you that already, by bringing carbon down through subduction. And it also exposes fresh rock continuously that can be weathered. So by erosion on the continents and topography, and also mid-ocean ridges that continuously produce fresh rock, fresh basalt, you are continuously allowing for this cycle to take place. So that's what I just said. So the idea behind this new tectonic setting is heavily inspired by work that Jeff Davis did for IO a few decades ago, where they explore with Thomas O'Reilly, they explore how thick could the basalt layer be, how thick could the crust layer be at IO, by looking at this cartoon where you have partial melt down below that ascends into magma onto the surface, and then you have this subsidence, this continuous subsidence bringing things down. And so we took that idea and explored how would that connect to an atmosphere that has CO2 and needs to keep the amount of CO2 at the right level to enable habitable conditions over long periods of time. And so we broke down our planet into three major reservoirs. We took the atmosphere and the ocean as one reservoir. We took this basaltic crust as another reservoir, and then this mantle. And so the idea is that they're connected with one another. And so the mantle outgasses continuously because the tidal heating produces melt that it sends. And then on top of it, it keeps erupting and erupting, and that keeps subsiding. At some point, it reaches back into the mantle. So instead of this horizontal conveyor belt that we have on the Earth due to plate tectonics, this is more of a vertical recycling environment. And then the weathering would happen because this basalt, if you have an ocean on top, this basalt would weather through this sea weather. For our purposes, a continent might not be important, but I'm learning here that for life, it actually might be important, so we can stay there. So let's see what are the governing equations. So the first thing is that we need to understand how CO2 and temperature are connected. So we do this through an energy balance model that says, okay, the energy that is received by the planet from the star has to equal the ability, the amount of energy that the planet is able to radiate away. And so graphically, that's that equation is shown here. So this is a model by Hack Misra and the casting group that was performed this year. And it shows the flux as a function of temperature for what the planet can actually radiate away. That's the cooling part. So the higher temperatures it radiates higher. And then how much it receives from the sun. If it's a sun-like star, you have here this orange line. Therefore, if you're looking at a sun-like star, these 2 points, this 3 points is where you have that equality. But this point is unstable, whereas these two are stable. So in the case of the Earth, the simple model explains why we have a Balmy equilibrium most of the time, but we've also had snowball Earths that have also persisted for some time. Then the red line shows you the difference between a G star and an M star, and stars radiate in the infrared more, so there's a difference there. And actually, this case that you see here is due to the albedo. But then we also thought about another way of expressing this balance, because it's been shown by numerical models that actually in M stars, there might not be this equilibrium, that you might not transition quickly to a snowball Earth, that you just progressively maybe move the front of snow, but you don't transition fast, so that this would be a more appropriate description. Okay, so moving on to telling you about the governing equations, we just need to keep account of where the carbon goes. So it's this process. So we take the atmosphere and ocean as one reservoir, and the sources are the outgassing that depends on the resurfacing velocity, and the sinks are the sea weathering, and the sea weathering has a weak dependence on the amount of CO2 in the atmosphere, but has an Arrhenius dependence with temperature. That also depends on CO2 in the atmosphere. I should tell you that some people in the community do not have taken this as not really dependent on temperature. And for this mechanism to work, it really needs to depend on temperature. So I think, and it's been more in the recent years that has been more established that there is a temperature difference, but I just want to say that caveat out there for please. Okay, so that takes care of the atmosphere. The next reservoir is, for example, the basaltic crust. So the sources of anything that's coming from sea weathering, and the sinks is what's going down into the mantle. And we do the same thing for the mantle, and then these are the equations that govern the system. And if you're uncomfortable, if you're scared enough, you'll see that the atmosphere and ocean reservoir has a dependence on only the atmosphere of the CO2 in the atmosphere. So we need a new equation. Oops, it's a solubility equation that tells you if you have CO2, how much CO2 will partition into the atmosphere and into the ocean. And that's through this Henry's solubility law. Okay, let's see what else I need to say. Yes, so we have the equations, and we can solve the equations if you have some initial conditions. But there's a few decisions we need to make. We need to make a decision on the resurfacing velocity, and we need to make a decision on the thickness of the basaltic layer, and also the sea weathering at some equilibrium. So the thickness of the basaltic layer and the resurfacing velocity come from the tidal heating theory. So this is based, again, Jeff Davis' work. Oh, sorry, I forgot a video there. And the resurfacing velocity will depend on how much tidal heat flux you have. And they're connected through this A parameter tells you how much tidal heat flux contributes to the total heat flux. But it's really unknown. Without a very careful thermal history of a planet, including the eccentricity, how the orbit evolved, how it dissipated, we won't know exactly what A is. And so because it's such a large parameter, so such an unknown parameter, we take this as two independent quantities, but acknowledge that they are dependent on one another. So we take some values. These are, for example, the values for the TRAPPIST-1 system. These are all in the habitable zone. And then we also need to make a decision on the sea weathering, and we can do it two ways. We can say, okay, we really don't know what the sea weathering is on the present day Earth, but we can explore what kind of sea weathering we would need to have to ensure that the temperature and the pressure in the atmosphere are the same as the Earth, pre-industrial values. And so that's the first condition that I impose, and say, okay, what would the sea weathering have to be? And then look in the ranges that have been calculated where that range would lie. So that's what you see here. That's the sea weathering that we would need to have, and it depends especially on how much carbon the planet has. And we don't really know how is that established in the planet. So that's one way we can do it. The other way is, okay, we say we know exactly what the Earth's value is. This is taken by Mills 2015, and say we are just going to use that and the spreading rate of the mid-ocean ridges here, and then take that as face value and extrapolate that and calculate other equilibriums. What would be the new equilibrium for other planets? And that's what you have here. And if you do that, you see that if the planet has low carbon content, you have temperatures that resemble something more like the Earth. But if the planet has a lot more carbon, then you start getting into really high temperatures. Bad for us, not bad for microbes. And then once you made a choice on that, we can integrate the equations. We first do it without star evolution, so the sun is kept at a same value, and we see that it would follow the same sort of thing that we think happens on Earth. So if we start with a very disequilibrium state where we have very cold temperatures of very little CO2 in the atmosphere, and all the carbon in the basalt, for example, then it needs to be processed to make it back into the atmosphere. So the way it does it is that the outgassing, so it first needs to get a little bit into the mantle, and the outgassing outpaces the weathering, and at some point, if you start with a snowball state, it will deglaciate completely, it overshoots. This has been seen as well for models on Earth, and then it'll settle back into an equilibrium. We can do this with different initial states and conditions, and the behavior is all the same. The time scale for this depends on the sea weathering rate, and it's about between 10 and 100 million years. But in reality, the sun has gotten brighter over time, and that's actually why they invoked the carbon-silicate cycle to explain the faint young sun. And so this is the sun that's gotten brighter, and this is an M star. So the M star differs from the sun because it actually starts really bright and it cools down. And so the habitable zone moves from further out to further in. So the planets that were now in the habitable zone were one time too hot to be there, too hot to be habitable. And so they raised the question of, can you have water? And some other studies have said that yes, they can contain some water still. So what we did is then look at the evolution back in time, no, forward in time actually, to see if you can establish an equilibrium still when the sun is dimming in luminosity. This is in a log-log scale. In this case, we start from very hot. The planet has a lot of CO2 in the atmosphere. From the hottest point, we could use the EBM model, and then it does the same thing. It actually cools because in this case, it's the sea weathering that outpaces the volcanism or the decasting, and then it reaches the equilibrium. So it's a very simple model to show that it's actually the equilibrium is stable. You can linearize around the equilibrium points, ask if your Jacobian, ask if your eigenvalues are positive. That's what you see over here is that the eigenvalues, and when you go through the map, you see that the eigenvalues will always be positive. Sorry, well, this kind is always positive, they'll always be negative. So the equilibrium point is actually stable, independent of the details, dependent on exactly what the surface velocity is or the thickness of the salt layer. So this seems like a robust way of enabling this carbon-silicate recycling that might be important for having thermostat in other planets. And so the conditions for this mechanisms are that you need liquid surface on the water. You need liquid water on the surface. You need liquid water on the surface. So you need to be in a habitable zone of a planet that produces milk continuously. And so you're really restricting yourself to M-DWARFs, thank you. Because, and not single planets, you want them in resonances that you can pump each other's eccentricity to keep tidal heating going for billions of years. So the TROPICS-1 system is a perfect planet for that. And then your sea weathering needs to be high enough to be able to recycle the carbon content. For planets that have too much carbon content and their sea weathering might be limited, maybe due to kinetics, then the outgassing will outpace sea weathering, and you wouldn't restore, you wouldn't have an equilibrium. So in summary, what we're trying to propose is that in the absence of plate tectonics, because these planets might not exhibit that, just like Io's tectonism, you might enable habitability to this tidally induced tectonism. I already explained to you the conditions. It's a nonlinear system that has a very stable equilibrium, and the time scale for this is about 10 to 100 million years. So any events that are much shorter or much larger, like a M-star flare, much larger, like the brightening of the sun that happens really billions of years, they don't really matter. They don't have an effect. And with that, I'll take any questions.